is here on the screen. So the check marks are subjects which we went through, and we stopped about here. So if you have any pressing questions about these items, let me know. All right. So if not, then we'll go along with this, and we will continue with a little bit of a fermionic physics. I'll tell you a little bit about kinetics, hydrodynamics, out-of-time order correlation functions. Maybe, if time permits, something about disordered systems, but we'll see how to go. All right. So a very brief recapitulation of what we talked on Monday. So we started from the von Neumann equation for the density matrix, many body density matrix, which may be formally solved by applying evolution operator from the left and from the right. And what I argued is that this expression silently, not even silently, but it necessarily assumes thinking about evolution along with closed time contour. Then we discretize this time contour, we write an effective field theory action written in terms of field living on top and the bottom. And then there is a convenient Keldysh rotation, which goes to sum and difference of these two fields. And in terms of those, the action has certain fundamental properties, namely normalization. Without quantum fields, it should be zero, and time reversal is manifests itself in the fact that the action is an odd function of quantum component. And then as any odd function, it's not surprising that it's zero, then phi quantum is zero. So then what I try to explain is that this very property immediately implies a certain structure, which is known as causality, of correlation function, namely some of them are zero, some of them are purely retarded, namely they exist only for t larger than t prime, some advanced, t smaller than t prime, and another component is known as correlation. And I wrote this correlation function this way, which somebody pointed out that that's a mistake. A better way of writing it is this. So this is the same convolution as here, but the order, I mistakenly tell you something which is not good at definition. So sorry for that. Take this instead. All right. So then we talked that you can write a Dyson equation, pretty standard, up to this additional matrix form of all green functions and self-energies. So the Dyson equation also has matrix form, and the most interesting component, matrix component of it, has to do with this distribution function f, and that's nothing but quantum kinetic equation. And finally, we talked about saddle points. So I argued that there is always one trivial, not a trivial, but one obvious saddle point where all quantum fields are zero, and the classical ones obey whatever classical physics is at hand, whether it's Newton, Maxwell, or anything else. And as a corollary of it, I mentioned that any non-trivial instanton kind of field configuration should have a non-zero quantum field. And another corollary of it is that both phi classical in principle exist in a classical limit, namely, if would Planck constant be zero, this equation will be still intact. But quantum components should be thought of being of order h bar. So if H bar is 0, then quantum component never exists. So that we would be always sitting in the classical kind of world, and phi quantum would be 0. So with this, we can proceed forward. And what I want to tell you a few words is a theory of classical stochastic systems, and how does it come about from this Keldysh, Schwinger-Keldysh framework. And the way to think about it is the following. Suppose I would try to expand my action in effectively in powers of H bar. So then there is 1 over H bar in front of the action. So the first term will have this form. And if that would be the end of the story, then I would immediately, of course, reproduce this statement that the classical saddle point is given by certain operator acting on classical fields, and that is equal to 0. But we can go, if H bar is not 0, we can proceed. We can have a next term, which is quadratic in phi quantum. Now, I sort of told you a minute ago that the action should be an odd function of quantum component. Here it is obviously even piece. Now, why is that? That's because we have in mind a system which is connected to some buff, and we integrated out this buff, and that broke time reversal invariance. So once the time reversal invariance is broken, then there is no any more a requirement that action should be purely odd function of phi quantum. An example of such term is demonstrated by this diagram. We talked a little bit how these diagrams are built last time. Then the thing to sort of appreciate, and I ask you to believe me about this, it's not difficult to show, that if you think about high temperature physics, namely all relevant frequencies are much less than temperature, then this in principle non-local function become effectively local. It behave like delta function of t minus t prime, and it's proportional to temperature up to some coefficients which I don't want to talk much about. So it's basically temperature, nothing else. That's formally come from the fact that cotangent of omega divided by 2 temperature, you expand at high temperatures, and the first term is proportional to temperature. All right, so if you believe that, then you can do what is called Hubbard-Stratonovich trick or transformation. So you take this part of an action, you put it in the exponent, and you have term like this. And this term you can formally write as a Gaussian integral over auxiliary field, which is traditionally called psi. So you see it's a Gaussian integral, so even I can know to do it. And if you do it, you basically complete the square, you immediately find this left-hand side. But now, look, there is a good news, because I have still this piece of an action sitting in the exponent, and I have this piece of an action also sitting in the exponent, but they both are linear in quantum component of my fields. So if I have a linear function sitting in the exponent, and I do functional integral over phi q, what I get is a delta function. So what this delta function tells me, yeah, that's what I just said. So what this delta function tells me is that instead of some operator acting on classical field being equal to 0, now it's equal to this auxiliary field psi. which you should think about as stochastic noise sitting on the right-hand side of this equation. So whatever equation you have now, whether it's Newton or Maxwell or Gross-Pitaevsky or whatever your favorite Landau-Lifshitz Gilbert equation, whatever you work on, you can always supplement it with noisy right-hand side. And this noise will be, in first approximation, Gaussian. And the Gaussian correlation function of it is determined by our self-energy. Okay, so that's how we upgraded sort of noiseless classical mechanics to noisy quantum, still classical, but noisy classical mechanics. Okay. Yeah, there are some interesting issues about it related to regularization and possible supersymmetry. I will not go into details of that, but if you're interested and you know something about it, you're welcome to ask me privately. Okay, so let's consider an example. So let's consider classical system, purely dissipative. So I have viscous friction, first derivative, velocity, if you wish, and the force. And I completely disregard Newtonian inertia. So there is no acceleration in this classical mechanics. So there is only friction and external force. So potential may be anything, with potential V may be anything. So we'll think about something of that shape. Why? Because what we want to think is that particle is sitting here, but due to thermal activation, it has a chance to go out and escape this potential value. Okay, let's see how it works. So we have our action, which has this linear piece in phi quantum. So phi quantum times this operator. And then there is a quadratic piece which came from integrating out some thermal buff. Okay, so that's pretty ugly expression, but there is an easy way to make sense of it, namely compare it with familiar Hamiltonian action of classical mechanics, which looks like PQ dot minus Hamiltonian, which is some function of Q and P. So now, if completely formally, I will associate phi classical with Q and phi quantum with P, then we'll have a Hamiltonian. We'll have a function of two variables, canonical pair, and we'll have an action which formally has this form, PQ dot minus Hamiltonian. Instead of PQ dot, I now have this piece. All right. So what is it good for? It's good because we know how to deal with Hamiltonian systems. We know that energy is conserved. And what we need to do, we need to go and think about phase space. So phase space is here. So it has a coordinate along the horizontal axis and quote unquote momentum along the vertical axis. And then there are lines which correspond to constant energy, namely constant Hamiltonian. So what we immediately notice is that, as we argued before, that classical physics is encoded by phi quantum equal to 0. And in that case, our Hamiltonian is equal to 0. And here is this line of phi quantum equal to 0. It has two stable points. This one, which corresponds to the minimum, and that one, which corresponds to the unstable maximum. And the classical dynamics along this line is encoded in the arrows which go out of an unstable point and they go into the stable point. Okay, but what you notice is that that's not the only opportunity to have zero energy. You can also nullify this bracket, and that will be also a line of zero energy. And if you plot it, you will find something like this. Okay. Now, according to Liouville theorem of the classical mechanics, if one direction is compressing, the complementary direction should be stretching, and the same here, one is compressing, one is stretching. So you see immediately that using this trajectory, you can go from the minimum up to the maximum. That's not what noiseless classical mechanics does. But once you have your noise encoded in this sigma Keldysh, you do have an extra trajectory. And this extra trajectory, what it does, it takes you from here to there. Okay, now what is left is to calculate the action along this trajectory. That's an easy thing because Hamiltonian is conserved and it's equal to 0. So we don't have to worry about this big bracket. So the only thing which we have to worry about is this, integrated over time. So that means that we simply have phi quantum d phi classical, and that's nothing else but area. Okay, so all what we have to do is to calculate the area shaded in this picture. Very good. How do we do it? We know equation for phi quantum from here. So you substitute it here. It's 1 over sigma Keldysh times this, and now the integral is trivial. And what you have is maximal potential minus the minimum of potential divided by temperature. So this is nothing else but activation exponent. So what we find is that our theory recovers thermal activation, but it recovers it in a sort of funny way. You look for a semi-classical, let me say, solution, but not the classical one, which is leaving at phi quantum equal to 0, but another one which allows you to have some non-trivial quantum component of your fields. And that brings you the thermal activation. Now you can go one step forward and you can really look at this now as a Feynman quantum mechanics. And you can say that P and Q are actually operators, and there is non-trivial commutation relation. And that implies that P is should be understood as derivative over Q. And there is a quote-unquote Schrödinger equation behind it. And this Schrödinger equation is actually funny because our Hamiltonian is funny. It's not P squared plus V of Q, which is a standard Newtonian Hamiltonian. It looks very different. And if you quantize it and you write it in this way, then what you find is so-called Fokker-Planck equation, which give you equation for classical probability distribution function of your stochastic variable phi. Okay. Now, you may be alert that in case of Feynman, this equation is written for an amplitude, and in our case, I'm telling you that it's written for the probability. That's look a little bit suspicious. But remember that we have double contour. So in some sense, one part of the contour describes psi, and the bottom part of the contour describes psi bar. So therefore, a closed time contour, it describes, as we know, it describes density metrics. which is about probabilities, not about amplitudes. So therefore, after quantizing this theory, we ended up with a differential equation, sort of Schrödinger equation, but for the probability, and that's a familiar from stochastic physics Fokker-Planck equation. Any questions?
Yes. How do you assure that the probability will be positive definite?
Well, yes. In a sense, well, again, because you have two branches of a contour, and one of them works as a complex conjugate of another, you're bound to deal with positive definite quantity. But probably simpler way is to derive equation and convince yourself that if you start from a positive definite P, then in a process of evolution, this property remains. Okay. It is rooted in the fact that our initial von Neumann equation preserved positive definiteness of density metrics.
But is it true for arbitrary potential V?
Yes.
Okay.
Well, look, if you have potential like this, the escape, right? So then you can worry about normalizations and things like that. But people in classical stochastic physics know very well how to treat Fokker-Planck equation for this potential. So in that sense, I'm not telling you anything new. In particular, if you want, you carefully want to find a pre-exponential factor in the Kramer's formula for escape time, you should deal very carefully with Fokker-Planck equation and its boundary conditions. But it is all here and all true.
Okay.
And I'm not saying everything is trivial. You need to work.
Okay,
but
thank you.
As a conceptual thing, it's all here. By the way, from here, you can immediately see that Boltzmann exponent, which was written in a previous slide, exactly nullify this bracket in a Fokker-Planck equation. Now, you can go further and, yeah, no, right. So you can go further and you can use this machinery to describe so-called fluctuation relations. So probably the simplest of them is so-called Jarzynski relation, and it's about the following. So suppose you have this Langevin equation with potential which is time dependent. Then and some noise, of course. So then you can define work which is performed by this external force during some time between tau t initial and t finite. So since there is noise here, this thing is not deterministic. It is random. Depending on realization of the noise, you can have bigger or smaller work performed by external force. So there is some distribution function of this work, which we don't know in general. But what we can ask ourselves by some reason is what is a expectation value of this particular exponent. And it's very important that it's work divided by temperature with coefficient -1. If I would put -2 or -1.5, here in the exponent, then I would not be able to make any strong statement at all. But one is special, and I'll explain you in a sec why. Because you write your functional integral, Keldysh, essentially. So that's what we had before. Let's see. So this piece is what we had before. But now I have my observable, and I add it to my functional integral in this way. So now I can go ahead and play the same trick and quantize and obtain the modified Fokker-Planck equation for probability distribution function. And what happens is that our Fokker-Planck equation acquire an extra term, and this extra term is fine-tuned in such a way that Boltzmann exponent with time-dependent potential will be a solution, right? So normally, for normal Fokker-Planck equation, if you have time-dependent potential, then of course this is not a solution. Only for static potential, this is a solution. But we play the trick by choosing proper observable. We managed to modify our Fokker-Planck equation due to this term in a very special way that Boltzmann exponent with time-dependent potential is still a solution. And once we have this solution, we can have a statement about this expectation value, which is valid for any potential, any noise, and is very general. Whether you want to know this expectation value or not is another question. So most probably not. It's not an easily measurable observable, as I can explain. But as a formal statement, it's sort of cute that despite of having completely non-equilibrium system with time-dependent potential, you still may have some exact statements. So this type of statements are known as fluctuation relations. And what I'm trying to tell you here is that they are can be completely naturally derived from this functional integral framework. Basically just few lines calculations.
Can I ask one question?
Sure.
So here is the capital T temperature?
Capital T is temperature, yes. This capital
T
and this capital T is temperature.
I see. So, but I mean, under the time-dependent potential, so here it is assumed that the system is under thermalized. I mean,
no. So, well, yes, very good. So it assumes that there is a buff at certain temperature connected to your system. But then the system is driven out of equilibrium by time-dependent potential. Okay? So the system is in contact with thermal buff with a given temperature, but you drive your system. Okay? So
yeah, I see. So here, so the temperature T is not changing.
Temperature is a constant. It's a characteristic of a buff. We don't do anything to it.
I see.
But we act with time-dependent force on our system, on our particle. Okay?
Oh, thanks.
Very good. So let's continue. Okay, so in another application of this kind of ideas is in the field of so-called reaction models. So you consider some agents which are sort of classically quantized. It can be molecules, or it can be animals, or it can be people, or it can be stock options. Anything you want to think about, which is measured in discrete integer numbers. So then you can write certain classical, what is called master equation for the evolution of a probability distribution to find n agents at time t. And in general, this master equation has a form of so there are rates of going from n prime species to n species, or there is a rate of going from n to n prime. And then you multiply it by corresponding probabilities, and you sum over all possible n primes, and that gives you the incremental time change of your probability distribution. So pretty much any problem in population dynamics or kinetics of molecules or whatnot, excitons and semiconductors, you can write in this way. For example, you can have rules like this, that if A meet A, they annihilate each other and go to zero. And then A may die, and then A may multiply itself. And this lambda, mu, and sigma denote rates, relative rates with which these processes take place. So then you can easily go ahead and write down what is this rate function from n to n prime. So with rate lambda and this coefficient, which tells you how many pairs of A and A I have in my system. With coefficient mu, it's proportional to n, because any of n species A can die. And again, the process sigma is proportional to n, because any of them can multiply. Something like this. You can invent infinitely many different examples. Okay, so how do you proceed? Yeah, sorry about that. You formally write this master equation as the following thing. If you want to go from n to n plus r, you can write it as a shift operator. So if you act with e to the minus r, you think about n now as a continuous variable, but if you act with operator which is r dn, that means that whatever function you act on will be shifted, the value of n will be shifted by r units to the left or to the right, depending on this sign. So so you can formally write this master equation as a differential operator using this shifting identity. And then you can proclaim that ddn is your momentum operator, like in quantum mechanics. So then all this thing you can call Hamiltonian. Of course, it's not a Hamiltonian, but you can call it this way. And it's an operator. It's depend on operator P, which is this, has correct commutation relation with variable n. And that's a thing like this. But once we have that, so by analogy with the Fokker-Planck equation, we can write our beloved action. So we call n as a classical field and p as a quantum field, and then write down the Hamiltonian action. So this way you can really encode in a field theory way any problems which involve reactions and for example, diffusion of species. In particular, many people are interested in phase transitions in these systems. For example, in this particular example, if death rate mu is sufficiently large, then sooner or later everybody will die. But if mu is not too large, then the system will live forever and sort of have some stable, in average, stable population. So this is a computer simulation of precisely this model in one dimension. So you have one dimension x, and you have diffusion along this direction, and vertical axis is time, and then you play this game numerically. So if mu is less than critical, your system proliferate. If it's larger than critical, it dies in some finite time. And you can think about this phase transition between the two at some critical value of mu, and that will be similar to second order phase transition. You will, if you define correlation lengths, which are sort of defined here, if you can see them, you will find that at the transition correlation lengths diverge, and there is a field theory which describe it. So there is a Hamiltonian written in terms of classical and quantum field, and its phase portrait, which we already saw in a previous, few minutes ago, schematically looks like this. Now you change your parameter mu, and your phase portrait changes. So that's the critical point, and that's the dead phase. So again, this is the live phase with some stable particle number here, and that's the dead phase. So that should be compared with an equilibrium pictures. So in equilibrium, we know that there is a Landau theory of the phase transitions, and there is a Landau free energy or Landau potential. And as you change some parameter, your free energy evolves, and you go from double minima to single minima, and then to something like this. So in non-equilibrium situation, you don't have a potential, but instead you have a function of two variables, because you have two branches of a contour to begin with. And the way to visualize it is not plotting the potential, but plotting the phase portrait of your effective Hamiltonian. So this picture comes as a non-equilibrium analog of this picture. Okay, and then playing with this, you can classify all kind of phase transitions happening in these models, depending on sort of topology of your Hamiltonian. So there is a lot to talk about here, but I just want to give you an impression, a clue how to think about it. So in particular, what you can do using this machinery, in addition to thinking about phase transition, you can think about rare events. So the example which I happen to like is so-called Lotka-Volterra model, and it's a model of interacting rabbits and foxes. So rabbits can proliferate, and foxes can die from starvation. And then there is a kind of physics view on fox multiplication, namely if fox meet a rabbit, then rabbit disappear, but fox multiply. I understand that's not how it happens in nature, but that's the model. So this model, if you think about it in a kind of mean field analysis, predicts an infinite stable cycles where population of both species oscillate from bigger to smaller, and these oscillations go forever. However, if you do numerical simulation with discrete species, foxes and rabbits, then instead of this, what you find is this stochastic trajectory. Here we started at this stable point, and then it goes in a spiral. Actually, it goes in different directions, spiral, clockwise spiral. And then the spiral becomes bigger, and then even bigger. And then at some point, the last rabbit die, and then foxes cannot proliferate, and all foxes die from starvation, and you arrive to empty system. And that takes a certain time. And for example, you want to know how long in reality the system can live. So what you do, you write your Hamiltonian, which has classical rabbits and quantum rabbits, and classical foxes and quantum foxes. You write your Hamiltonian, and you go ahead and you analyze it. It's not very difficult and actually quite beautiful. And you can precisely reproduce all the features of these numerical simulations.
Sorry,
All right.
what do you mean by a quantum animal?
Well, what do I mean by
Do you
quantum?
mean a superposition of a fox and a rabbit?
No, of course not. Look, like here, I used to have this A's, right?
Mm-hmm.
And they were measured in integer number n.
Yes.
But to have an effective description, I had to say that this n is continuous.
Oh.
And there is a conjugate variable, which I call phi quantum, which is sitting here. Okay.
Yes.
So although I had integer number n of animals A, I don't know who are those animals, my description include two fields, 2 degrees of freedom. One is just continuous version of my n, and another, which I call quantum by analogy with Schwinger Keldysh, which is necessarily here, as you see. Say precisely the same thing with my foxes and rabbits, right? So classical rabbits is just continuous extension of number of rabbits, and there is a corresponding quantum field, and the same for foxes. If you don't like these names, you can use any other names you wish. But I like those.
But usually the canonical conjugation variable to number is a phase. Is that right?
Yes.
So that means you are extending the number into a complex number?
Let me think a sec. If I treat them as complex or real. No, I treat them actually as real.
Yes, but you have P. So in phase space, I
have P, but, and it would be a phase. Look, P is always sitting in the exponent.
Right.
But this is now, if you wish, non-compact phase. It's a exponent without I.
Okay.
Okay, and that comes from the fact that I'm not dealing with unitary quantum mechanics, but I'm dealing with a dissipative stochastic system.
Okay. Thank you. Thank you.
So the price to pay is indeed this non-compact nature, if you wish, of a phase. Very good. All right. So the so there is one more topic which I may want to cover. Okay, let's try to do it. Which is known as counting statistics. So what I argued is that expectation value of some classical variable can be obtained from generating function by taking variation with respect to quantum source and then putting source fields to 0. Okay. Then you can calculate, let's say, fluctuations of your variable, whether it's classical fluctuations or quantum fluctuation. It doesn't matter to me for now. So fluctuations are given by second derivative of your generating function with respect to quantum source. And again, I put source field to 0. Okay. But suppose I don't want to find first moment, second moment, third moment. Suppose I want to find entire distribution function. Okay. Phi is a random fluctuating observable. I do my measurement and I can find something. And in average, this is this. I have fluctuations which are determined by this, but in principle, I may ask what is entire probability distribution function, such that to calculate moments, I need to take this probability distribution function and take a convolution of it with phi or phi square or phi cube or what have you. Okay, so what you can easily observe just from here that this probability distribution function is nothing else but Legendre transform of your generating function. But the generating function calculated at finite quantum noise, quantum source. So if you want to calculate this, you need to introduce source field, which again, it may be scalar potential, it may be vector potential, it may be magnetic field, it may be whatever you want. But you need to allow it to have quantum component. What means quantum component? That means that it is different on a forward and backward branches of the contour. Okay, which is of course unphysical, right? Because all physical external fields which we can generate in a lab, they are by definition precisely the same on a forward and backward part of the contour. But if you want to find the probability distribution function of your observable, again, classical or quantum, you need to allow external fields which has this weird property. They are different on forward and backward branches of the contour. So once you do it, you need to work somehow, calculate this generating function, and then so the remaining is easy. You just do Legendre transform and you have your distribution. Right. So by the way, that once we have external quantum source, a simple classical solution is configuration is not a solution anymore. So you need to work harder. You need to find the solution which contain both classical and quantum fields. And it's not easy, but sometimes you can do it. So the most probably famous example is so-called counting statistics of quantum scatterer, or for example, tunneling barrier or quantum chaotic cavity or any quantum object, quantum dot. So it is characterized by certain scattering metrics, and you have, your electrons incoming and outgoing, and they're related by scattering metrics. And what these people showed, actually 30 years ago by now, is that if you want to find probability that precisely n electrons will pass through your scatterer, this probability is given by transmission coefficient into the power n and reflection coefficient to some other power. And here is a combinatorial factor, number of combination of little n over whatever, n factorial divided by little n factorial n minus n factorial. Okay, so-called binomial distribution. So your electrons obey precisely binomial distribution, exactly the same as a coin which you toss with, heads or tails. So electrons play precisely the same game. Any questions? Yeah, go ahead. Okay. All right. So we have about half an hour left. Let me tell you a few words about how you extend this machinery to fermions. It's pretty straightforward, but there are a couple of sort of conceptual points which are worth to have in mind. So if you ever find yourself working with this, it may help you.
Okay, and the other question is it's interesting that you talk about a flux in rapid case. That what is there any meaning for the Hamiltonian in that system? Like we know if we call it energy, but in that model, what's the meaning of Hamiltonian?
Well, let's see. So Hamiltonian is a way to encode in a certain way these reaction rates. Okay, so W is a reaction rate, and you build your Hamiltonian out of reaction rate and these non-compact phases. So it's a differential operator of infinite order because this derivative is sitting in exponent. So it's infinite order differential operator acting on your probability distribution function. And you call this operator a Hamiltonian, or you may not do it because it's of course not a Hamiltonian, but it has many common features with quantum mechanical Hamiltonian. That's probably the best I can tell you. All right. So, but you're right. It's sort of amazing that you can write a Hamiltonian, quote unquote Hamiltonian, for rabbits and foxes. I like it. Anyway, fermions. So fermions, Hilbert space is spanned by fermionic creation and annihilation operators, which has these obvious properties. There are only 0 and 1 states. There are no 2, 3, 4 fermions at the same state. So those are sort of simple object. You can, for one fermion, you can encode it as 2 by 2 matrices. But if you have n fermions, these matrices become already 2 to the power n times 2 to the power n. So it's extremely unpleasant to work with this as matrices. But as an operator, they are very nice and convenient notation. You can define coherent state pretty much like in the case of boson, with a difference that instead of complex number, you have a Grassmann number. So this psi is a Grassmann number which anti-commute with each other, and psi square is equal to 0. So again, for any Hamiltonian or any other operator, if it is a normally ordered in terms of C and C dagger, you can immediately calculate this matrix element. You just formally substitute this psi and psi prime, and you got this. Calculation of this overlap is completely trivial. It's basically written here, but you're welcome to do this exercise for yourself. And the thing which I really need is the resolution of unity, which again very similar to bosonic one, but it includes these integrals over Grassmann variables, which is a funny object. It's defined, completely defined actually by these two properties. Sort of, it's defined as a game, if you wish. You just define these objects, but they work as actual integrals, sort of to all extent and purposes. All right. I mean, I understand that that's terribly fast. So if you never saw it before, you probably will not be able to follow. But I assume that by now it's a relatively standard material for usual quantum mechanical classes. All right, so if you are still with me, then you proceed as before. You have your partition function, which you define as an evolution operator along the closed time contour. You discretize it, you introduce resolution of unity in each discretization point, and you write it formally in a continuous way as opposed to discrete notations. And you have your action sitting in the exponent, and this action has a form of, for simple Hamiltonian at least, as a quadratic form of fermionic fields living here, and quadratic minus quadratic form of fermions which live along the backward part of the contour. Exactly same as for bosons, but instead of complex fields phi, we have Grassmann, time-dependent Grassmann function, if you wish, or field psi. So one thing to notice here is that because of this artificial definition of an integral, all fermionic integrals are always convergent. There is no such a thing as divergent fermionic integral. Okay, so therefore you don't have to worry that this psi bar being in some sense complex conjugate of psi. It's not, it's just a notation. So psi bar and psi are two completely independent, different Grassmann numbers, and I choose to call them psi bar and psi just for convenience, to have analogy with bosons. But they are not complex conjugated in any sense of the word. And that's actually important because now you want to do your Keldysh rotation and go to sum and difference of the fields. And the way you do it is different from bosons, namely for psi. So take a pen. So for psi, you do it precisely the same way as we did for bosons. Nothing new here. But notice that I don't call this field classical, and I don't call this field quantum. I call them 1 and 2. And there is a deep reason for that, because there are no classical fermionic fields. For example, you cannot write classical equation of motion in terms of fermionic field. So therefore, calling this combination, for example, as classical would be nonsense. You shouldn't do it. It's only good for bosons. Now you go to psi bar fields and you see that you do it in a sort of different way. Namely, here you have minus and here you have plus. Although naively you would think that you should do opposite. So that's a notation. Again, psi 1 bar and psi 2 bar is just notation. I can choose them any way I want. So this particular way of choice was done by these two gentlemen long ago, and since then it's become completely standard. So it's good to have in mind. And there are many convenient features of this choice. So I will try to point them as we go. All right, so you reformulate your theory in terms of psi 1, psi 2, psi bar 1, psi 2 bar, and you define your correlation functions in terms of this psi 1, psi 2. And it has causality structure, but notice that it's quite different from bosons. So it still has zero retarded advanced Keldysh components, but they are shuffled in a different way in this matrix. So for bosons, we had these fields called classical and quantum, and I explained to you that that's how it fundamentally should look like. Here, because of this different convention of transforming psi bar fields, the structure is different. You still have purely retarded upper triangular matrix in time, space, and lower triangular matrix here, and zero here, and some Keldysh function here, but you see they all shuffle. Okay, what's good about this? So what's good about this is that you can immediately conclude that if you consider product of any number of these matrices and you look for trace of it, so this is a diagrammatic representation of this for free green functions. Trace represent this kind of loop. So you go from T1 to T2, from T3 to T2 to T3, and then from T3 back to T1. So that's why initial and finite time is the same. And you take a matrix multiplication along the way. So then you see that on the diagonal, you will have a product of either all retarded function here or all advanced functions here. Okay. Now, if you have a product of free retarded function, then you know that, let's say here, T2 is larger than T1, T3 is larger than T2, but here T1 should be larger than T3. So that's a contradiction because T2 is larger than T1, T3 is larger than T2, and therefore it's larger than T1. But this green function wants T1 to be larger than T3. And therefore, this object is always zero if all green functions here are purely retarded or purely advanced. So this trace is always exactly equal to zero. And that's an important thing. You will see how it works in a minute. Okay. So my computer is stuck. All right. Okay. So then the rest of it is sort of standard. Keldysh component in equilibrium can be written as difference between retarded and advanced, and Fermi function Away from equilibrium, you define quantum distribution function in this way. And by the way, another nice property of this fermionic matrices is that you can always write it as a rotation of purely diagonal matrix. And rotation matrices know only about distribution, quantum distribution function, but not about anything else. And in practical calculation, that's an extremely useful concept to do. But that's just, in parentheses. If you're not doing calculations with this, forget about it. Okay, so now let me explain how fermions interact with bosons. So suppose I have some external field, for example, scalar potential. Vector potential may be written in exactly the same way. So the way fermions interact with bosons is through two gamma matrices which act in this 1-2 fermionic space. So you have combinations like this: fermion, gamma matrix, and again fermion. So quadratic, what's the name of it? Quadratic forms of in terms of fermions. Gamma matrices are very similar to what you have in Dirac equation, and this AB space is internal fermionic space. Bosonic classical and quantum indices are very different. They are not the matrix indices. They are labels of these two gamma matrices. So what I'm trying to emphasize here, that bosonic indices and fermionic indices, they operate in different spaces, right? Like in general relativity, you have Christoffel symbols, and the lower and upper indices of the Christoffel symbol are living in a very different spaces. But never mind. All right. Right. So what this identity means is that if all my fields are purely classical, all my bosonic fields, so those are bosonic fields, okay? And if all these bosonic fields are purely classical, they come with unit matrix. So this matrix is just one, nothing else. So then this fermionic loop is bound to be zero. If you have any number of classical, only classical bosonic field entering fermionic loop, it's always zero. Okay, and if I have time, I will try to explain to you that that's not accidental at all, and it's has to do with fundamental normalization of our partition function. Any questions? No, right, then let's continue. Then you proceed pretty much the same way. You can define self-energy. It's a matrix again. You can define Dyson equation. It has, again, standard form with metric structure. You substitute definition of quantum distribution function, and you end up with quantum kinetic equation, written in terms of self-components, retarded, advanced, and Keldysh components of self-energy. That's same as for bosons. So, for example, if you have fermions interacting with some bosonic field, it may be Maxwell or phonons or whatever you want. The simplest self-energy looks like this, and you can immediately see what it is. So this is one fermionic vertex, which we had here. So that's this object. And that's another fermionic vertex. So we expand our action to the second order in fermion-boson interaction. And then we take expectation value of two fermions here and two bosons there. Okay. And from here, you can immediately sort of read out what is your self-energy. It has this 1, 2 indices in fermionic space. And just looking at that, you immediately read it out. So it's this, and this is your fermionic green function. This is bosonic green function. Where alpha, beta is classical quantum, and A, B, C, D, they are 1 and 2. Again, if you ever do this calculation in practice, I try to show you that it's not scary at all, and you can do it sort of quite easily. If not, then again, forget about it. Okay, so in particular, if you have your interacting fermions, then the diagram you consider is this, and it boils down to right-hand side of your kinetic equation, which known as collision integral, and you can easily read it out from expression which I had in a previous transparency. So that's the form, and you can sort of associate this with this line, and this you can associate with what with this line, and this guy you associate with this line. So with a little bit of practice, you can sort of learn to derive it in pretty much in no time. Now, if you recall that Fermi function is related to this tangent by a simple relation, then the simple algebra convert this lengthy bracket to something more familiar. So 2 occupied states, 2 empty, minus 2 other occupied states and 2 empty states. That's precisely the same expression, which you see in many textbooks. So far, so good? Any questions?
I hope so.
Hi, I have a question.
Sure.
Yeah, so in traditional way to derive the Bosons equation, we sometimes we need to assume the Markov approximations.
Can you repeat it, please?
In traditional way, when we try to derive the Bosons equation, sometimes we need to invoke the Markov approximations. So is it obvious where the Markov approximation here?
Yes. Well, yes. So initially, my distribution function is a matrix in time space. It has 2 time indices. So it has t and t prime, right? Now, what I do, I do Wigner transform. So this particular form is written already after Wigner transform. So it's now depend on energy and center of mass time, t plus t prime over 2. And you do what is known Maillard expansion. Okay. So when you go from matrix and matrix multiplications to algebraic multiplications of Wigner transform, that's where you secretly involve your Markov approximation.
Okay, I see. Thanks.
Okay, very good question. All right, so so now a couple of words about hydrodynamics. So hydrodynamics follow from this slide, basically from this kinetic equation and this collision integral, by noticing that our system has certain conservations, namely it conserves number of particles, usually if it's not superconductor story. It conserves particle momentum if there is no external potential, and it conserves energy if there are no time-dependent fields. So what these conservations tells you that these three quantities are conserved in any binary collision. So two electrons collide, but number of electrons, total momentum, and total energy is conserved. So this is reflected in these identities, which you can easily check once you know your collision integral. You go ahead and you trivially check that that's true. Okay, very good. So what do you do with that? So you go to your kinetic equation, and now you take a summation over all states k, and the same, of course, on the right-hand side. You do summation over states k, and then the right-hand side is 0, and the left-hand side gives you something. Then you do the same, but you multiply it by k, right? And of course, here you also multiply it by k. Again, right-hand side is 0, and left-hand side gives you something. And finally, you multiply it by epsilon k, by energy, and here epsilon k. Again, right-hand side is 0, and left-hand side gives you something. So these left-hand sides give you three equations, which is maybe written in terms of, so the first one coming from here will give you continuity equation. The second one will give you essentially Navier-Stokes equation coming from here, from momentum conservation. And finally, the equation coming from energy conservation will give you something which happens to be heat diffusion. And all these quantities like density, momentum, energy, and fluxes of density, fluxes of momentum, and flux of energy is written here. You can easily work it out from here. So that's the way you derive hydrodynamic equations from the kinetic equations. Okay.
Sorry.
Yes.
Why the sum over collision integral is 0? The first one.
This one.
Yes.
Because number of particles is conserved. Right.
Does this rely on the isotropic property of the space?
No. It relies only on particle conservation. So what it is that if you look at the bottom line here, once you do summation over k, the in processes are exactly compensated by out processes. So if particle go out of state k, it should go to some other state. It cannot disappear.
Thank you.
So that's how it works. So this way you derive hydrodynamics. This is not specific to Keldysh technique. I'm just telling you some basic facts about kinetic theory. You need Keldysh to derive the kinetic equation, but to derive hydrodynamics, you don't need it. All right. Okay, so do I have time? Yeah, I have 3 minutes. So out of time order and butterfly effect. So some people argue that to describe propagation of chaos in a system, one may want to use so-called out of time order correlation function. Namely, the correlation function where some observable is taken at time 0 and time t, 0, t, again t. And I remind you that they do not have to commute. They, in general, are not commutative. So the order is important. So if you want to describe such correlation function, you need your Keldysh contour, but more complicated one. Keldysh contour with 4 branches. So you have your observable here, and then you have it here, and then you have it again here, and then again here. So you need to develop Keldysh machinery, but your matrices is not 2 by 2, but rather 4 by 4. Okay, but you can do it. It's not that difficult at all. In particular, your distribution function is now a matrix. Yeah, notations are that this, upper Keldysh contour is called up and lower Keldysh contour is called down. And sometimes people call it upward world and down world. So in this up-down space, your distribution function became a matrix. So it has up, up, down, down, up, down, and down, up components. And you can easily show that in an integrable, someone has not muted the microphone and there are noises. Can you please mute it? Thanks. So in equilibrium, if you have integrable system, let's say non-interacting fermions, you find, so that's your standard Fermi function, which we always had before. And there are now extra 2, which has simple form. And you can derive your kinetic equation. And this kinetic equation, you have standard one for up, up, and down, down. That's precisely the one which we had before. But now there is an extra component. You have a kinetic equation for up, down, and down, up. And they look similarly, but if you look at them carefully, they're actually very different. In particular, the in term has this up, down, up, cubic kind of combination. And the out term is linear in up, down, and everything else is only about up, up, and down, down. Okay, so that's a very different balance between in and out processes. In particular, these hydrodynamic identities, which I showed you before, they do not work here at all for this type of an integral. And what you can show is, so first thing you can convince yourself that this equilibrium values indeed nullify your collision integral. So equilibrium is good, but equilibrium is not necessarily stable, unlike the usual case. Namely, there is another solution, trivial one. This guy is equal to 0. And this guy is equal to 0. And you can easily see that it also trivially nullifies your collision integral. And this is actually a stable solution in presence of collision. So you can show that solution of kinetic equation has a form of a front. And this front is between equilibrium solution and trivial zero solution. And this front propagates ballistically, even if everything else like charge, spin, heat, magnetization, if everything propagates diffusively in your system, the chaos, if this function describe chaos, chaos propagates ballistically with constant speed. And this was called a butterfly effect, thanks to butterfly causing a tornado analogy. And from here you can calculate velocity with which this quote-unquote butterfly tends to propagate. So this thing will be explained in a second edition of my book if you're actually interested. But there is a beautiful paper which has all of it presented. So if you're interested, you're welcome to find it and learn more about it. And actually, Google realized it now in their quantum computer. They can really measure this, but out of time order correlation function and how it propagates in experiment in an array of qubits. All right. So I had something about disordered system, but probably I will skip it. Okay. Any questions?
Okay, thank Peter. We're now open for question. If it's audience is outside, please come to the table. If online, you can speak directly.
Sorry, can you go back to the page of butterfly?
Sure. It's not far away.
So I assume that characteristic behavior is at the level of expectation value. Is that right? You check some expectation, the time evolution of some expectation value and find such effect. Is that correct?
Well,
For butterfly effect.
In principle, yes.
Okay.
So you want to. So if you want to find butterfly velocity, what you want to find, let's say, at x equals 0, these two, and these two at some x. So if you have one-dimensional system, which what Google does with their qubits, they form a one-dimensional array, and then they perturb it at site 0, at time 0, and then they propagate it in space and time, and then they do it backward in time here. Sorry. Yes, so that's what they measure. Some correlation function which depend on x and time. And they find that it's proportional to x minus vt. So there is a front, so some function of this combination. And this velocity is called butterfly velocity. So you can. Okay.
Thank you.
Mm-hmm.
So I have another questions. For this collision integral, if I want to go to classical limit, do I just take the temperature to be very high, or do I need to do something else?
Yeah, pretty much. If you go to high temperature limit of wait, wait, do I want to say it or not? Yeah, probably that's not bad. If you want to go, let's say, from degenerate electron gas, you want to go to classical plasma, you just go to, you know, high temperature and you deal with plasma. Yes.
Okay, thanks.
Can I ask one question?
Sure.
So it's regarding the universality class in non-equilibrium physics. So recently, I mean, nowadays people are interested in the new universality class. I mean, existing only at non-equilibrium setting. So, I wonder. I mean, in equilibrium, I mean, there is a very systematic way to understand this universality by using RG, right? But
yes,
I just wonder, so is there some kind of systematic approach like maybe RG in non-equilibrium system in this Keldysh formalism?
very good. Very good questions. Now let me try to go back. Right. So in equilibrium, what you do once you understand this topology that you want to go from potential with one minima to potential with two minima, you write the simplest potential which does it, which is sort of phi square. Yeah, I'm not very good at writing with my mouse. So phi square plus phi to the 4, right?
Mm-hmm.
And you argue that those are most relevant terms in your RG.
Mm-hmm.
So you can also have phi to the 6, phi to the 8, but they are less relevant, right? So that's how you get an idea what you want to phi to the 4 action to renormalize, right? So here, if you go to the left, that's precisely the same thing. You write the simplest Hamiltonian, which has this topology, and that will include 3 straight lines, 1, 2, and 3. So that will be some cubic combination of classical and quantum fields. And you argue that those are most relevant terms. And that gives you a certain universality class, which is known as directed percolation. Or high energy people like to call it Redge field theory. That's precisely the same. And most of this non-equilibrium phase transition indeed belong to this directed percolation symmetry class, but not all of them. You can have different topologies which will require sort of different field theories, and they protected by symmetries. You cannot, they are not reduced to directed percolation if there are extra symmetries. So this is directed percolation, but if there are extra symmetries, you may have something else. And they have different universality classes. They have different critical exponents, and you can write RG, and it's very beautiful science how it is done.
But here, I mean, I'm wondering. So this is phase space of some fields, right? So A, C, L, and AQ.
Yes.
But in usual RG, we draw RG flow in the phase space of coupling constant. So
Yes.
is it same as that, or
same here, right? So you write corresponding Hamiltonians with some coupling constant. Then you separate your fields on fast component and slow component. Both fields, classical and quantum, have fast component and slow component. You integrate out fast component. You look how it renormalizes your coupling constants. and you go. But what this pictures inform you is what kind of coupling constant you want to put in your action to begin with. Okay, so once you realize it, looking at this picture, then you can start running your renormalization and see how they renormalize. And that will tell you critical exponents, which, if dimensionality is sufficiently small, they're quite non-trivial.
I see. Thanks.
You're welcome.
Okay. Any further question? So they, if not, let's just thank the speaker again. Thank Professor Kamenev. And